And I think it's most important that you all get multiple times to see Q-learning. So we're going to do this whole thing again with Q-learning, with really trying to solve an optimal control problem. So see, the problem with this is, what are you going to do with this? If you wanted to solve the Rover problem, how would you apply this? You take rho equals 0.8, you'd run this where X would not be that three-state Markov chain, it would be the information state. You know, that's okay, you could do it. and you would run this to get an approximate solution to that dynamic programming equation, but you'd use that for policy iteration. So you'd have to update your policy and do it again, and update your policy and do it again. And that's annoying as hell. So why can we learn the optimal policy or approximate the actual? This is for a fixed policy we're trying to approximate right now. There's no optimization yet. This is for a fixed. This was just one Markov chain, no control. All right. So, which is what you do in policy iterations. In policy iteration.
Before we're trying to find like V, which is H, right?
But it was not H star. It was H for a particular policy.
Yeah.
Which is what you do in policy iteration. So this is a tool in approximate policy iteration. I have a policy. I want to, in policy iteration, yeah, so we're going back to the controlled model. So in policy iteration, what do? If you give me a policy, I then define a transition matrix. All right, so that's how we define policy iteration. First, you give me a policy. First, I define a transition matrix for the Markov chain with that policy, which is the kind of thing we've been studying here. And I define a cost function. That's the cost function for this policy, you know, because U is, after all, just equal to phi n of x. So I can eliminate U. You know, and so then I have to solve. I'll just write down abstractly. It's C plus P n H n plus 1. There's a beta missing. So you have to solve that equation. And so if we were doing this and X was not the three-state Markov chain, but it was the information state, then good luck trying to solve that, except for this gentleman did. You know, approximately. But I mean, so one application of TDE learning is to approximate the solution to this. Okay? But anyway, if you could solve it, you get your new policy. Okay, and you know, this is an awesome algorithm, and you know, it's the HNs are monotonically decreasing, and you know, it's just you know, you saw that it's just instantaneously fast, or how quick it is. All right, so that you could do that. So you know, you could do that. The only trouble is, you might get into some trouble here. Is that in the update stage, this could be very, very complex. You know, it might be that even evaluating Pu hitting Hn plus 1 could be very complex, as it is in the homework. You know, if the state is the information state, this is a monster. So you want to avoid that. So Watkins came to the rescue there. So Watkins solved this problem. Although he didn't, it's still a frontier. I mean, this is a frontier. If anybody says that this is old stuff, I think it doesn't exist yet. You know? So Q-learning. And I mean, his thesis was 89, right? I think, God, again, I should have written this down in my notes. Anyway, the notes I will hand out will give you the correct dates. I think it was 89, his PhD thesis. But his goal was not approximation, it was computation. But we're going to extend this. And not with any justification. So some of the things I'm going to say won't work. But, you know, it's an open field. There's so many, there are more open questions than solid theory. You know, his goal was computation. All right, and let's do it. So we have to go back and not look at policy duration, but go back to the discounted cost optimality equations. Okay, there's a discounted cost optimality equations, and you'd be tempted to say, PUH is a conditional expectation. I can do the same things. So let's try that. All right, let's just try to copy what I did before. So this says that so remember before I plugged in x equals xt, well, here I'm taking the min, so I can't replace u by ut. But I said that's a conditional expectation. So let's do it again. How about that? So this is equivalent to this. It's a bit hard to write down.
What do you mean? The first one is 0?
This is, oh, no, sorry. I wanted to be able to write it in the same way where I'd like to. Remember before I had said something was 0, and then I had the conditional expectation, and I did the Galerkin stuff. Do you see how it all gets screwed up? Before I had 0 equals something, and I multiplied through by a function of time, and I'm going to have a minimum outside. I won't be able to take expectations of both sides. I'll have an expectation of minimum. It'll become a horrible mess. Yeah. I won't know how to get an algorithm. Well, actually, well, I mean, good point. We should try it out. It would be, yeah, you're right. I mean, you're right. We could multiply this by a. No, hold on a second. It's a minimum of a u, and I'm going to take a function of time inside and bring it inside. It'll have, I better make sure it's positive valued so I don't change the signs of the minimum. But even that can change things. No, I'll be in trouble. I'll be in trouble. If I try to take a function here, and everything will be screwed up. Yeah. No, it won't work. Yeah. Yeah. Well, you scared me there for a second. No, but if I multiply this by a function of time, it will be well, if it's positive value, it'll be okay. You're right. Because, multiplying this by a positive number isn't going to change anything. Yeah, that's true. But what does it mean? God. Well, anyway, that's a good question. I mean, to me, it never even occurred to me that you probably could come with an algorithm. You'd have to. I don't know. I can't answer that right now. That's funny. No, let's stop for a second, because I think it is obvious. I'm just getting confused for a second. Well, can we come back to that? Because I can't give you an answer right now. I think one of you, it'll be obvious in a moment. When I tell you Watkins' ingenious trick, maybe Watkins wasn't a genius and we're all fooled. Right now I can't answer your question, but I'll try to come back to it. But his ingenious trick was to look at the term in brackets, and that's what he called the Q function. We now know that there's motivation from that from old optimal control. This turns out to be very much related to the Hamiltonian that comes up in optimal control. So there'd be sort of motivation for looking at that in that way. It's also sort of related to our linear programming approach, where we looked at a function of two variables instead of one. There's sort of a connection there as well. You can make that precise. So there's lots of reasons to doing this, but Watkins' motivation was to have a minimum inside of an expectation. So we'd have one expectation without a minimum outside. And yeah, it'll be clear. There's no way you would be able to get an algorithm like you can in this way. There's no way with a minimum outside. It'll be clear. So, why would I do that? The reason I would do that is that, and now bear with me, because this is always hard, this always blows people's minds when they see it. I'm defining this function of two variables to be Q star of XU. What's its minimum over U? Yeah. So we know the minimum over U of Q star of XU, which I'm going to call Q lower bound star of X. So whenever you see me put a lower bound, it means I've taken a minimum. So you give me any function of two variables, I'm going to take its minimum and get a new function. You all agree that's H star of X. All right? You've all agreed with that, and you can't take that back. Therefore, all right, you can't take it back. You agreed with me. Now some of you can object. I didn't cheat. I said Q star of XU was C of XU plus beta PU H star, but H star is Q lower bound. That's it. So we have a fixed point equation you know, for the Q function, just like we had a fixed point equation for the H star, but by this clever trick, we have a minimum inside the expectation. And now we can do our Galerkin hacks. And we couldn't before, and we're going to have to think about why, but we couldn't before. I think it will be obvious in a second. So, therefore, I'm going to have 0 equals Q star of xt minus. And yeah, that's, yeah. And I don't want to give that a name yet. Sorry. I can't give that a name yet. All right. And so if you give me, and I'll write this down again. So this is at 0 equals the expectation. And can you imagine me having to write this all down again? But I have to. Minus Q star of xt ut plus C of xt ut plus beta Q bar star of xt plus 1 times zeta t. And that's not a theta, it's a 0. For any bounded zeta t, which is ft measurable. All right. So that's a brilliant trick. Now, the thing that's awesome here, absolutely awesome, is this expectation is with respect to the optimal policy? I hope not. I don't know it. So what's so cool is that this is policy independent. No matter what policy I put in, this is true. Any stupid policy, this is true. That is what, you know, caught people's imagination. Just, what the hell? Because then you could do the Galerkin hack. You know, then I'm going to replace a star by a, you know, a parameterized family of functions. I'm going to come up with some way of coming up with test functions here, these eligibility, you know, vectors, whatever, and I get an algorithm, and there we go.
What do you mean by it's true for any stupid policy?
I can, yeah. I mean, where did I use optimality of the policy here? You know, so I had a fixed point equation for this, then I made a definition, and then I interpreted the fixed point equation as a conditional expectation. Well, this is true for any policy that's adapted. You know, that's, you know, UT is it could be randomized too, but any randomized adapted policy that you want, right? Yeah, so that's the cool thing. Is now it means that I can put in some stupid, crazy policy, doing this wild crap, just make this rover bounce around, and then watch the thing, and approximate the solution to the optimality equations. It's completely wild. Yeah.
How did you pull the expectation to bring those two parts into the expectation?
No, it's the same as before. Remember? The expectation of this thing, the expectation of that is the same as the expectation of that. This is no difference than when I looked at TD learning. No difference at all. Exactly the same steps.
Because xt, ut, or ft measurable?
Yeah.
You can take them outside of the expectation.
Oh, no, not that. No. All I did is I've got 0 equals something. I took the expectation of both sides. So, and I also multiplied by zeta t. So I used the fact that zeta t is ft measurable, so I could take it inside.
Okay.
Yeah. Which is the same trick I used before.
Well, what happened with the conditional
Well, that's a smoothing property. The conditional, the expectation of zeta t q bar star of xt plus 1 given ft. That's the thing you're worried about. I multiplied both sides by zeta t. I'm going to get that because I can take the zeta t inside because it's a conditional expectation. You're worried about this. Well, if I take the expectation of that, that cancels out. That disappears. It's just equal to the expectation. Let's take that in. Yeah. So it's no difference at all. Yeah. And that's it. So now we don't have to do anything now, right? Because you know the program. You're gonna come up with some parameterized function of Q functions. That might be hard to think about, but to remember where it comes from. So I know for the speed scaling model that 8 star looks like x to the 3 halves. I know something about the dynamics. I know how that's going to affect it, and I add on a cost function. So if I have structure for 8 star, I have structure for this. But yeah. Yeah.
This holds for an infinite dimensional?
Yeah, it doesn't, I mean, well. So here now we're in fantasy land because there is no theory for anything. So I said that Watkins' goal was to compute 8 star. He took a basis, which was everything, the indicator function of every state action pair. And there's theory. So beautiful theory. Outside of that class, there's almost no theory. People do things and they work, and nobody's figured out why. It's just except for a few classes of problems. So I have a paper on deterministic systems. So continuous time deterministic. X dot equals f of xu. And you think, how could this be applicable? Well, why not? If it's a deterministic system, I can still put in a noisy input. And so basically like an LQR problem, I'm trying to get to the origin. I can still put in like a mixture of sinusoids as an input to explore, or white noise or something, I can do something crazy. And there's theory for that that's just really crisp and pretty. And for what's called optimal stopping time problems, like in finance, I want to know when to stop and cash in my options. That problem, there's a Q-learning theory that's really crisp and elegant. But nothing is complete as there is for TD learning. And it's all because of the fact that this thing here, I could have a linear parameterization for Q, but then when I take a minimum, this will be a convex function or concave function of theta. The structure though that gives you hope. The fact that again, if this was a linear function of theta, if we had an approximation, when I take a minimum, I get a concave function. That's structure that should be valuable. But good luck on proving anything. You just have to go and try it out. And so that's why I feel a little unfair giving you a homework assignment where there's no theory to justify it. But I do know enough about. I think when you have problems, we'll be able to fix them. And that's the last time I'll torture you. This will be the last, last thing. So where's the algorithm? Just let's come up with a Q lambda algorithm, right? I mean, shall we? So I'm gonna define something that doesn't exist. So here's an algorithm that does not exist except for one special instance, which is Watkins' algorithm from '89. Okay, and I'll let you tell me what I'm going to do. Right? I'm going to do the same thing. I'm going to have a basis function for Q. So now I'm going to have functions of two variables. It's really tempting to write plus c of xu, because we know that's in there. And we could put that in there, but let's make it linear instead of affine. You know, I could always tuck in a c of xu in one of these or something, I don't know. And then I can define eligibility vectors. Right? So I could take my basis vectors. You see, these are d-dimensional vectors. You know, plug in my observations at time n+1. Again, I'm just taking and putting it through a low-pass filter to get the eligibility vectors, and then just take that and plug it in. Right? I'll just take that. And you guys are all going to make me do this, aren't you? I don't like that n. You maybe use n. I think it should be n+1. That's what they use in the literature, isn't it? I screw the literature. I want to put n+1 because it's in the future. I'm going to change the notes. It's the whole point was that you were taking something in the present multiplied by something in the future, and we're making use of that fact. That should be emphasized. So dn+1 now is this mess. And that's it. Phew. All right. So try it out. It'll blow up, unless you do things right. So it's proven to converge in one case. So Watkins lambda equals 0. So the eligibility vector is the basis function. Okay? As far as I know, nobody's proving anything if lambda is not 0. There's nothing out there. You know, it might converge. I don't know. It's an open question. And also, those basis functions are just indicator functions of every possible pair. So what you do is you enumerate all possible inputs and states, all possible pairs. So, you know, it's not a big deal in the Grover problem. If you have full observations, you've got 3 states, 2 actions. So 3 times 2 is 6. So there's only 6 possible values. But when we go to the partially observed problem, this is, you know, even if you've been, it's going to be millions of terms. You know, I mean, thousands of terms. All right. And then you can prove convergence. And the way you prove that this works is there's an ODE, and that ODE is awesome. It turns out the ODE you can analyze, and you can see it's consistent. It's not hard to see that. You know, it's a very nicely behaved ODE. Because there's a very strong theory of stochastic approximation, and if that ODE is sufficiently stable, you know that the original algorithm is consistent and stable as well. But you violate that, out the window. But I know there's a theory waiting to be established. I know it, and and some of you, if you go on academia, will probably help to create it. It's just the thing is that a lot of people have gotten so successful in making it work and making money consulting and impressing their friends with magic tricks. It hasn't attracted a lot of people who want to do the analysis in a way. That's the thing. So it's not too many people have actually gotten their hands dirty to work on this. So that's why there's a real, really not enough going around. But damn it, in this, in that rover problem, for example, with partial information, given we have structure about the value function, it's concave, and then we know something about what the policy should look like, we should be able to come up with a function class that'll work pretty well. The only problem is stability of that ODE. You go and you do this without that thing. It's hard to get your head around that ODE. But I bet it'll work. I bet that you take again, there's some sort of positivity hiding here. There's this ugly dynamics. The minimum here is screwing things up compared to the analysis before, but there's a beta there that discounts it. So the negative term here helps. So I think you'll still get a contraction effect, and you'll still get stability, even though there's no theory yet to say anything. Yeah. All right.
So the sum there goes from...
This is an iterative algorithm. You run this for 100 million steps.
No, the sum, where you think it goes into given data, you have the sum.
Where's the sum?
Right above.
Oh, right there. Oh, yeah. I mean, there's D. It was always in D.
Okay, so...
nothing's changed. Yeah, just like before. Yeah, just like in T. So everything here is identical to TD learning, except for you end up with this strange minimization here on each time step. But before you run, just real fast, because I want to say this a few times. Imagine now you've got this toy. You've got to, forget all about scientific discipline at this point. You have to realize what a fun toy this is, because you can walk up to that rover problem, and do whatever the hell you want now. You can pretend the state is my observation now, my observation one time step ago, or my observation 2 steps ago, plus the last 2 inputs. Call it the state. Pretend it's a controlled Markov chain. You observe, you can run this algorithm. I mean, I told you the first lecture, there's no such thing as a Markov chain. F is not equal to MA. If F equals MA, prove it to me. If it costs that much money to do a controlled experiment to check that F equals MA, it's a meaningless thing. Friction's not linear, right? But we pretend it is. And so it's so much, that's why people have so much fun with this. It's so easy to code. You pretend something stupid is a state. And look at this, where do you use the transition matrix? There's nothing here. You never have to do anything. You have to perform a minimum and run. So that's why this is so popular. You can just try this out and see what happens. You see what I mean? Unlike value iteration, you have a model. You've got to hit V n by P and then take them in and all that. Model free, and so it's oversold like mad, but it is a fun toy. Hey, can you see? Can you imagine how trivial this is? Oh yeah, sure, but this you don't need a toolbox. Look at that. Yeah, I think there is. Yeah, but I think you're right. But you don't. I mean, yeah. So have fun.